Okay, welcome to day 3 and 4 of the virtual Ascent field trip. So to recap what we've done on day 1, we are here in the Ascent window. This is the Moyne thrust zone that extends down from Loch Eriboll all the way down to the Isle of Skye, dividing the stable foreland, the Lewisian stable foreland to the west, from the Moyne Metamorphic hinterland to the east. And the Moyne thrust zone is this zone of complication where the whole of eastern Scotland is thrust over the stable foreland. The thrusting goes from east to west. So what we did on day 1 and 2 was look at the stratigraphy across the foreland here. We looked at the Lewisian basement gneiss, the Torridonian cover, the Cambro-Ordovician sedimentary sequence, and those rocks are the ones that occur on the foreland, on the stable foreland, and also imbricated within the Moyne thrust zone. Right, so what we're going to do now on days 3 and 4 is concentrate on the Lewisian. This is the red on this old geological map of northern Scotland. It occurs all the way out in the Outer Hebrides and all the way along the northwest coast of Scotland, and it forms the oldest basement rocks to the Laurentian plate, which was attached to North America prior to the Atlantic opening. And these are some of the oldest rocks in the UK. On day 3 and 4, we're going to do little mapping exercises. The first day, today, we're going to look at the Scourie in an area just south of Scourie Bay, where we have all 5 metamorphic units in one small area. We will, at the end of the day, we will give you a field map that was made already, and we will ask you to do a structural cross-section across that map. Now, all the information is in this field guide, so make sure that you look at the field guide, and you need to have this with you when you look at the video on each day. We'll do a similar exercise at Amelvic tomorrow, day 4, where we will give you a field map that was already done, and we'll ask you to draw a structural cross-section across that area. We will also practice how to take strikes and dips in the field, and recording all the structural information that you need to do when you're out doing your mapping.
Welcome to the introduction to days 3 and 4 of the Ascent trip, Northwest Scotland, and we're going to see some really interesting rocks in these next 2 days. On these days we will see some really interesting rocks of the Lewisian gneiss complex, which is some of the oldest in the entire UK. These are deep crustal gneisses that formed the nuclei of Earth's first continents, and they have formation ages of around 3 billion years old. This is when these melts were extracted from the mantle, and they were metamorphosed at around 2.9 to 2.7 billion years ago. This is during the Archean eon. Now, they underwent several subsequent episodes of deformation and metamorphism, and you can see the entire history of these events in the Lewisian gneiss complex. Now, on this map, everything belonging to the Lewisian gneiss complex is in this reddish colour. Now, here's Inchinadam, where we've been staying for the past few days, and the localities that we'll go in these next 2 days are further north. The key locality for today, day 3, is in the region of Scourie. So here we have some of the oldest and highest grade metamorphic rocks. These are granulite facies, very high temperature and very high pressure as well. These will be 800, 900, maybe 1000 degrees centigrade and 10 to 12 kilobars. So they formed in a very deep continental crust. Now, typically these rocks are mafic and felsic granulites. We saw on the very first day on the Loch Ascent section that there's almost bimodality of composition. We have light-coloured felsic gneisses and dark-coloured mafic gneisses. Scourie, one of the localities, Scourie Moor in particular, exposes some really very fresh mafic gneisses. But there's a lot more to see. Here's an aerial shot of the rock types that occur at Scourie Moor. There's 5 units that you will end up mapping at high resolution mapping on the ground. We have ultramafic gneisses here. These are very dark coloured mantle material, rich in olivine and pyroxene, and some spinel. Mafic gneisses are fractionated melts that have been extracted from the mantle and then placed into the crust. These would be dominated by pyroxenes, feldspar, plagioclase feldspar, and some garnet if the pressure is high enough. The third unit is the felsic gneiss, which is a melt that's been extracted by high-grade metamorphism of the mafic gneisses. Now, these are characterized by the minerals plagioclase feldspar and quartz, and a bit of hornblende biotite. They contain some mafic minerals. The fourth unit in this area is a pegmatite. Now this is a K-feldspar and quartz-rich melt that's been intruded into these rocks. And the final unit is a trondhjemite. So these are plagioclase feldspar plus quartz with virtually no mafic minerals at all. They differ from the felsic gneiss by not having hornblende and biotite. So some of these rocks are metamorphic and some of them are igneous. The gneisses form the basement of the region, and the cross-cutting magmatic units, the trondhjemite, the pegmatite melts, these were intruded at some later point in time. And in the field you can see some really quite spectacular cross-cutting relations. And from the information that we'll go and look at and the measurements we will take, you'll be able to construct some cross-sections to try and work out what's happening in the subsurface. And very differently from the first 2 days, these will be a lot of ductile deformation features. There won't be so much of the brittle faulting and some of the folding that we've seen in the ascent window. Another major type of rock that occurs in the Lewisian gneiss complex is a set of Scourie dikes. Now these are ultramafic and mafic dikes of variable width, sometimes as small as a few centimeters, sometimes several tens of meters across. And they have a common strike. They're pervasive across the entire complex, and they're a very useful time marker. So these dikes intruded at about 2.4 billion years, which is after the first major episode of metamorphism and before one of the subsequent episodes. So some of the dikes, if they occur in the older Scourian terrain, are undeformed and unmetamorphosed, and some of the dikes that have been subsequently deformed by the Laxfordian event do show metamorphic fabrics, and they've been deformed in different ways. One of the dikes in the Scourie region is colloquially referred to as the graveyard dike, and this is a 50 to 70 meter wide mafic dike, and it does show some evidence of autometamorphism. There's some small veins where fluid has infiltrated the dike, and we have garnet growth and pyroxene and hornblende growth. In the field, you'll be able to map out the contact between this dike and the Lewisian gneiss, and you'll do some structural interpretation of its emplacement history. Now, the dikes themselves formed during periods of extension in the Archean when the crust was being pulled apart and magmas from the mantle were rising up to fill in these gaps. So some interesting features within the Lewisian gneiss complex are some high-grade ductile shear zones where the rocks of the Scourian have been intensely deformed. One of these in particular that we'll visit is the Laxford front, colloquially known as the multicoloured rock stop. Now here we can see a whole range of rocks. There's felsic gneisses, such as the ones that are pervasive throughout the ascent window. There's mafic gneisses here, which are interpreted to be highly deformed versions of the Scourie dikes. And there's also cross-cutting granite pegmatites, so K-feldspar, plagioclase and quartz-rich magmas. And these cut right across the foliations of all the other rocks in the region, showing that they're much younger. Now here's a map of the Laxford front area. The Scourie region, which we go to and do this mapping, contains lots of mafic dikes. Everything to the north of the Laxford front is lower grade and has been reworked in a later metamorphic episode called Laxfordian. And this occurs at about 1.8 billion years, 600 million years after formation of the first metamorphic episode. So we have this change in metamorphic grade across the Lewisian gneiss complex. The high-grade granulite facies Scourian area, and the Laxford front is a transition between the Scourian and the northernmost lower-grade amphibolite facies overprint. Now there's many questions asking what the Laxford front actually is, and this is an area that is actively being researched today. Some people might think it represents a deformation front. Maybe these old rocks are being remetamorphosed during a subsequent collisional orogeny, and deformation was progressing across the terrain, and the Laxford front represents where the deformation stopped. Other people might say it's a shear zone that has shown differential uplift of crustal blocks, and you're exposing deeper levels of the crust in the Scourian block, the granulite facies units, whereas in the Laxford, north of the Laxford front, it's a shallower crustal level. One of the localities that we'll visit, which shows the lower grade metamorphism, the metamorphic overprint at 1.8 billion years, is in Amelvic. Now Amelvic has the same rock types that we see in the Scourian, but they've all had their mineralogies changed due to subsequent overprinting. So the mafic rocks in Amelvic don't show pyroxene and plagioclase as much. They show a lot more hornblende. This is a lower temperature version during retrogression. The ultramafic rocks, instead of containing olivine and pyroxene, they contain talc and serpentinite. And some of the felsic rocks contain more abundant hornblende and biotite. These would be alterations of any of the orthopyroxene that existed at the granulite facies version. Now Amelvic is very structurally complex. All the rocks have been ductilely deformed, and there's very large folds in the area that you'll get the chance to map out. Now, aerial shots will help you out here, and we'll take some strike and dip measurements of the folds in the region and be able to construct cross-sections and maps. The final locality we'll visit just north of Amelvic is the Canisp shear zone, which is an equivalent amphiboli facies Laxfordian shear zone to the Laxford front. Now, what we'll do is we'll walk into the shear zone and make note of how the deformation fabrics become more intense as we go in towards the core. So on the Amelvic Bay, we'll see very little deformation. Grain sizes will be large and deformation will be relatively weak. Whereas moving into the shear zone, you'll see the fabrics become more intense, more steep, and the grain size will reduce. And interestingly, the fabrics are not penetrative in the shear zone. So we'll see some underformed pods and lenses of the protoliths that represent relics of the pre-sheared lithologies. Right, let's go and make some maps. Well, welcome to day 3 of the Ascent field trip, and today we've come to a locality just south of Scourie, and we're going to have a look at some of the high-grade gneisses in the Lewisian complex. So much of northwest Scotland and many parts of North America, Canada and Greenland formed a large continent, Laurentia, in the Archean, and the bulk of this continent was generated from magmas that were extracted from the mantle at around 2.9 billion years ago. These magmas were then subjected to various episodes of metamorphism, deformation and recrystallization, 2 of which we can see in the Ascent terrain here. So the Scourie rocks that we're standing on right now, these were metamorphosed at around 2.5 billion years. The rocks that we're going to see today were metamorphosed at about 2.5 billion years, and they reached granulite facies conditions, which is representative of the deep crust. A later deformation and metamorphic event occurred during 1.8 billion years, and this is the Laxfordian event, and that's characterized by lower grade metamorphism of the amphiboli facies. Now, in between these 2 events was a period of relative quiescence and stability, although a period of extension of the crust is characterized by the intrusion of mafic and ultramafic Scourie dikes, and we'll see all of these rocks during today's activities. Now, the outcrop that we're standing on right now exposes 5 rock types. It's really quite unique in the Lewisian complex, as we see all 5 in close relationship with one another, and this tells us more about how they all formed. These 5 rock types include ultramafic gneisses, mafic gneisses, tonalitic gneisses, which we previously referred to as TTG or grey gneisses, and we also have 2 igneous rocks, 2 intrusions that cross-cut these gneisses. These are pegmatites and trondhjemites. And the mineralogy, the colour and the structure of all these rocks are really quite different from one another, and it makes this locality ideal for mapping and sample identification. Let's go and have a look at some of these rocks.
Okay, this is the first of the rocks, which is called an ultramafic rock. Notice it's very dark. There's no plagioclase in this rock, so it's composed of mafic minerals only. And this rock comes from the mantle. The mantle is all ultramafic. This rock is composed of 2 major minerals. There's a very dark looking mineral here, and big crystals of orthopyroxene, probably the mineral enstatite. And there's a green matrix mineral, which is very prominent on weathered surfaces as apple green. This is olivine. So olivine is the main mineral of the mantle, and this rock type is called a Harzbergite, olivine plus orthopyroxene. Some of these have clinopyroxene in as well. Olivine, orthopyroxene, clinopyroxene. Rock is called a lertzolite, and the most depleted rocks are called dunites, which are pure olivine. So this is a mantle-derived rock, ultramafic. That means there's no plagioclase, no quartz in it. So it's very rare to get ultramafic rocks exposed on the crust of the earth, and most of these are either abducted ophiolitic rocks that come from the mantle in the Phanerozoic, but we're now in the Archean, so these could be either ultramafic intrusions or possibly even metamorphosed Scourie dikes.
The second rock type here is a mafic granulite. These are very dark coloured rocks with an interesting mineral assemblage. We have very large garnets, bright red porphyroblasts here. There's a matrix composed of 2 pyroxenes, clinopyroxene and orthopyroxene. and a pale coloured plagioclase feldspar. Now the mineralogy of these rocks is quite useful. The presence of garnet tells us that they formed at quite considerable depths in the crust, pressures exceeding perhaps 10 or 12 kilobars, which puts us at 30-35 kilometers down below the Earth's surface. Now these have the composition of basalts and gabbros, but of course they're metamorphosed equivalents thereof. So we would interpret these rocks to have been surface extrusions that were buried and then metamorphosed at great depth. Some of these garnet porphyroblasts have some really interesting microstructural features. Inside that cores we have large semi-euhedral clinopyroxene grains, and on the outside of the garnets we have these conspicuous corona composed of plagioclase. Now these metamorphic rims are associated with fluid influx from perhaps some crystallizing adjacent intrusions, and also decompression as the rocks are being exhumed towards the surface. So the garnet will break down and produce a lower version, a lower pressure mineral plagioclase in its place.
Okay, the next rock type is called the Trondhjemite. It's named after the city of Trondheim in Norway, and this is also sometimes called a plagiogranite. This rock is not a true plagiogranite, which has to have mostly plagioclase in, because this rock has a lot of quartz and a lot of plagioclase and a tiny little bit of mafic mineral, which is dominantly hornblende. So this rock, a Trondhjemite, is produced by fractional crystallization of a basaltic tholeiitic melt, and it's the final end product of that fractionation. First of all, you go from ultramafic, so you fractionate out to get to the mafic, and what is left of the final melt is a felsic unit, which is relatively minor. So this rock in field terminology is called a Trondhjemite, and that's it.
The next rock type in the area is a granitic pegmatite. Now this contains two main minerals with crystal sizes that are in the tens of centimeters to the meter scale range. It's really quite incredible. We've got a milky white quartz and a salmon pink potassium feldspar. And there's some paler parts of this feldspar that may be more sodium rich as well. But essentially it's a bimodal rock, potassium feldspar and quartz. This is quite an unusual rock for this area because it's very potassium rich, and none of the other rocks in Scourie contain much potassium, so it's quite a mystery as to how this rock came here. Normally, pegmatites represent water-rich melts that are highly fractionated from a precursor melt that may be more mafic in composition. But here, we would need to do some geochronological dating to work out if it formed at the same time as the gneisses, or maybe it formed at some time afterwards from an unrelated metamorphic event. One of the major rocks in this region and across the Lewisian gneiss complex as a whole is this felsic gneiss, a tonalitic gneiss here, which we've referred to previously as TTG gneiss. It's a characteristic feature of all continents, all cratons on the early Earth. Now in this rock, there's felsic minerals, there's quartz, plagioclase, and a small amount of K feldspar. And there's also some dark coloured mafic minerals too. Now, given that these are granulite facies rocks, these would be orthopyroxene with a small amount of hornblende, possibly some biotite if there's retrogressive phases in there. Now, interestingly, in these TTG gneisses, we can find pods of mafic gneiss. Mafic material like this, we might assume it to be a xenolith here. If these were originally tonelated magmas rising up through the crust, they could easily entrain parts of the country rock that they're passing through. And then these pods get suspended in the magma, and then the whole magma crystallizes. Metamorphism occurs, recrystallization occurs, and they're preserved now as mafic pods within this broader scale felsic gneiss. At this locality, we're going to get the chance to see one of the Scourie dikes. These are these large mafic and ultramafic dikes of variable thickness, some of them just a few meters, some of them tens or hundreds of meters wide, and they were intruded into the Lewisian complex in two pulses in a period of time in between the two major metamorphic events. So the Scourian metamorphism occurred at 2.7 billion years, the Laxfordian at 1.7, and the dikes intruded at 2 and 2.4 billion years. The example behind us, which is called the graveyard dyke, is 2 billion years old. Now it intrudes up against the felsic Lewisian gneisses, these TTG gneisses that we've been seeing multiple times on this trip. The dyke itself has a strike of west-northwest, east-southeast, and it cuts at almost 90 degrees across the foliation of the gneisses. So now we've moved down to the contact between the Scourie dyke and the adjacent Lewisian gneiss. And the foliation that's exposed in the Lewisian gneiss gives us a great opportunity to do some strike and dip measurements. Now a foliation is a planar feature within a rock, a two-dimensional fabric element, if you will. And here you can see alternating light and dark bands in the gneiss, which is the gneisso's foliation. So what we'll do is we'll measure the strike and dip of that foliation. So to measure the strike and dip of these foliation planes, we'll use the compass clinometer as follows. The dip direction is the maximum angle of inclination of the plane. So in this case, we can see that it's approximately in this direction, and we can measure the absolute dip of the bed by orienting our bezel with east-west aligned down the center of the compass clinometer. And this allows this little arrow to change freely as the angle of dip changes. So by placing it on the bed, we get an angle of approximately 38 to 39 degrees, and that's the dip angle of this foliation. Now the strike is the orientation of the bed that lies on the horizontal plane, perpendicular to the dip. Now in this case, we would put the compass on in the horizontal plane, move the bezel around so the red north arrow lines up with the actual arrow on the compass, and then we read off the strike direction in these two little yellow ticks here. So the bed is striking at 38 degrees and 218 degrees, which is approximately northeast-southwest. The other plane to measure in this instance is the orientation of the contact between the two rocks. And we can do this much simpler than with the foliation of the Lewisian gneiss. The strike of the contact between the two is done in the same way. We would orient the compass and then line up the north arrow on the bezel with the north arrow on the compass, and we will find out that the contact, the strike of the dyke, is at around northwest-southeast. We've got a bearing of 142 degrees and 322 degrees, which matches with the other Scourie dykes in the region. This Scourie dyke is approximately 40 meters wide, and it shows considerable mineralogical and textural variation from center to rim. Now, like many mafic dykes, it will have a sequence of minerals that crystallize as it cools. The original magmatic mineralogy for the dyke can be seen quite clearly in these coarse-grained members from the center. You get a lot of magmatic CPX, clinopyroxene, calcic plagioclase, and there's also some magmatic OPX in the original assemblage. Now, at the edge of the dyke, we have chilled margins, which cooled much quicker than the center, and these rocks, you can hardly see the crystals at all. So this texture we would call phaneritic, and this texture we would call aphanitic. And this sample here shows us something quite interesting and quite different. So we still see some of the magmatic minerals in here. There's the green clinopyroxene, there's the white plagioclase feldspar, and there's the black orthopyroxene. But there's also some other minerals that we see. Around some of the clinopyroxene grains, there's some black rings, and this is an alteration where hornblende has grown at the expense of clinopyroxene when fluids have entered the rock at some later stage. And one other thing that we see in this sample in particular is garnet. And garnet is not expected to crystallize from a mafic melt in these kind of dykes. We would interpret these to be some kind of metamorphic overprint that occurred at some later stage. And this is actually true. So, although this dyke was in place at 2 billion years, there was some deformation, some metamorphic overprinting that occurred during the Laxfordian event. At this point in time, once the dyke had solidified, fractures in the dyke allowed fluids to pass through. And these fluid planes allowed garnet to grow within the dyke itself. And you can actually see this very well in 3 dimensions here. So the garnet is the vitreous red mineral that occurs in this plane, which represents the passage of fluid. These garnets have been dated at 1.75 billion years, which coincides with a lot of the Laxfordian metamorphism and deformation that we'll see in other places in the terrain.
We've now had a close look at each one of the 5 different rock types in this mapping area at Scourie Moor. We've looked at the pegmatite, the big coarse-grained pegmatite, which is this thing in red. We've seen the mafic gneiss, the green, with pods of ultramafic gneiss within, wrapping around foliations, wrapping around folds. We've seen a prominent trondhjemite, this thing in yellow, which is intruding through the mafic gneiss. And we've also seen the main TTG gneiss, the felsic gneiss, the tonalitic gneiss in orange. So we've got this field map for you. This is on the PowerPoint. And what we would like you to do is to draw a cross-section across this using the structural information that you're given on the map and using your sense of the evolution of this area, which rocks came first and which rocks came last. Clearly the pegmatite cross-cuts the fabric in the mafic rock, so clearly the pegmatite was the final intrusive phase. But make an educated guess about the order of intrusion of all of these other mafic and granulitic rocks. This is a picture from the drone looking straight down on the mapping area. The pegmatite sheet is right here. I haven't marked on the offshoots, but there's two offshoots coming off here, which are these ones, and they cut the mafic gneiss. So this is a super outcrop map, and we just need you to draw a very simple cross-section. It's not going to be 100% accurate by any means. All the deformation is high temperature ductile deformation, but do your best and then give us a chronology of intrusion and metamorphism from first to last. Okay, well this is the Amelvic part of the Lewisian day, so this is day 4, and what we looked at yesterday was the Scourie granulite, and we looked at the detailed outcrop map of all the 5 different lithologies. These are the same rocks, but they've been affected by an amphibolite facies retrogression. So we have all the same units here, and unfortunately it's a bit rainy today. This is not a nice sunny day in Scotland like we normally are used to, but it's very atmospheric. There's waves out there and there's seals jumping, and it's really quite lovely in a different sort of way. But anyway, it makes mapping a bit difficult. So I'm going to show you a map that was done previously, and we are looking at a transect here along the coast in this direction here. And what we can see are the same units. So we're standing on the grey gneiss, the tonalitic TTG gneiss that we saw yesterday in Scourie. This is highly deformed. There's stretching directions going off in this way and very steep banding and a lot of ductile shear zone. The dark rocks over there are both mafic and ultramafic gneisses, but they have been affected by the amphibolite facies retrogression after the granulite. So this is all Laxfordian age amphibolite grade metamorphism. And we can't see it, but there's very tight folds in this rock as well. So you can see the map pattern here going round. That is a very tight synclinal axis, and there's a tight anticline axis here, which I was hoping to be able to show you and measure strikes and dips all around the fold axis, but clearly this weather makes it all a little bit tricky. So we'll hope for the best for the rain to ease off, and if it doesn't, we'll think of plan B, which might be the Coolag pub. So it's actually impossible in this rain to do some proper mapping. So what we're going to do is give you a copy of the field map here, and there's a lot of structural data on this map, and the task that we are hoping that you will do is to construct a cross-section across this region here using data from the field map. So this should be referred to not only the field guide but also the PowerPoint that comes with each one of these videos. You will be given this in the PowerPoint and explained how to construct a cross-section across this area. And the whole point of these mapping exercises is to go from outcrop scale mapping like we saw yesterday in Scourie to slightly larger scale mapping here in Amelvic, to detailed structural measurements on the outcrop. We're not going to be able to do that today, the conditions are just too bad, but we will do that at some other locality in the future. So yesterday we looked at the Scourie area, the Scourian granulites, and we looked at a super outcrop map where all 5 of those different lithologies were present. Today we're going to look at the Amelvic region, which is in the amphibolite facies overprint, the Laxfordian overprints of the Scourian granulites. All the same units, but different mineralogy, lower temperature minerals in there. The whole objective of this mapping exercise is to do the observation of the rock. What do you see in the rock? Everything you see in terms of composition, mineralogy, structure, you put on the rock on the map. And you mark in the strikes and dips, you mark in the fold axes, and you can use this information when you're back in the evenings for constructing a cross section. Remember, this is all ductile deformation. It's deformation happening at high temperature in the middle and the lower crust. So the folds are going to be not as organized and as simple as the fold structures we've seen in the Moyne thrust zone. In this case here, because we didn't see any mapping, it's pouring with rain and we weren't able to map. If you were able to spend 2 or 3 hours, this is a basic field observational map that you would have made. And from this, you can construct a section across there, which would look something like this. So felsic gneiss, the lines are the foliation planes, the boudins are the mafic boudins within the tonalitic gneiss, big tight fold structures in the mafic gneiss, and a synclinal axis plunging in this direction through the middle of the hillside up here, cut by lake faults, and this is the kind of cross section that you would construct across a Laxfordian type deformation area.
This morning we were in Scourie looking at the granulite facies gneisses. These very high temperature and very high pressure rocks are formed at about 2.7 billion years ago. North of the Scourie terrain is more Laxfordian metamorphism, which is lower grade amphibolite facies, and this is the 1.8 billion year overprint. Now the rocks that you see in front of you are on this transition between the 2 terrains, and this is called the Laxford front. This particular outcrop is called a multicoloured rock stop, and it has many different lithologies, many of which are the lower grade equivalents of the ones that we saw this morning. There are many different cross-cutting relationships which tell us about the order of metamorphic, magmatic and deformational events that have affected this area. One of the units you can see is this grey coloured gneiss, which again is the typical TTG gneiss we've seen all across the Lewisian complex so far. But instead of being granulite facies this time, it's been amphibolitized, so it has lower grade assemblages. Any of the orthopyroxene that was present in the Scourian examples is now replaced by hornblende and biotite, although the quartz and the feldspar still remain. These dark bands that you see are lower grade equivalents of the granulite facies Scourian dikes that we saw this morning. They've been thoroughly amphibolitized. So instead of containing clinopyroxene, orthopyroxene and rare garnet, instead now they're hornblende and plagioclase aggregates with a bit of biotite as well. Now there is one new rock type here that we haven't seen yet, and these are granites sensu stricto. These are the pink veins that cross-cut all of the previous examples. They intrude across the gneiss and the Scourie dikes, which tells us that these are one of the youngest phases to appear in the outcrop. These contain K-feldspar, plagioclase feldspar, quartz and biotite, and it's at the Laxford front going northwards where these granites appear, and it's one of the diagnostic indicators of lower grade Laxfordian metamorphism and deformation. Now, let's go over the road and have a look at the rocks in detail. This gneiss, the grey gneiss, is similar to the TTG gneisses that we've seen previously, but instead of having a granulite facies assemblage, now they have an amphibolite facies assemblage. As I mentioned just before, any orthopyroxene that would have been present has been transformed to hornblende, and some biotite will have grown as well as a result of the lower temperature metamorphic overprint. There's still a foliation in the rock. We still see the alternating light and dark bands, and this will have been one of the precursor rocks into which these other magmatic rocks have been intruded. The second lithology in this outcrop are these dark bands, these remetamorphosed Scourie dikes. Just like this morning, these were mafic dikes that are intruded into the TTG gneisses, and this particular example has been dated, and its crystallization age is thought to be 2.4 billion years, but its recrystallization and metamorphic age is 1.7, matching the rest of the Laxfordian deformation in the area. Instead of having pyroxene, plagioclase and some garnet, like the example we saw at the graveyard this morning, instead this has hornblende plagioclase and a bit of biotite and quartz. The third lithology in this outcrop is a granite, sensu stricto, so it contains K feldspar, plagioclase and quartz, with some dark material too. In this case it will be biotite. Now granite wasn't seen at Scourie this morning, but granite occurs in the Laxfordian deformation event. So although the mafic gneisses melted initially to form the TTGs, the granites that we see in the Laxfordian event are the results of melting of those TTGs. So it's a much more fractionated melt, and it represents a reworking of older crust. Hence, these granites cut straight across all of the units in this outcrop. They're younger than both the mafic dikes that have been remetamorphosed and the parent TTG gneisses.
So we're looking here at a Scourie dike, one of the same dikes that we saw in the graveyard up at Scourie. But this one is on the margins of the Scourian granulite facies and the Laxfordian amphibolite facies. And as we go towards the contacts in the traverse, these dikes are going to get progressively more and more deformed. So this dike is about 20 meters wide, and you can see from the texture of the rock here that it is still containing igneous textures. This is a classic Scourie dike with igneous textures, but the margins of the Scourie dike show ductile shear zones, which we'll look at next. And this indicates the beginnings of a dextral sense of shear during the Laxfordian deformation. So this is the margin of this Scourie dike near Amelvic, and you can see that this dark rock here is the metadolorite, which was the Scourie dike and has now been gradually deformed and remetamorphosed during the Laxfordian. This is the country rock, the grey tonalitic gneiss, and you can see the fabric in the country rock. The foliation is going like this, and it is clearly truncated at the margins of the dike. So the gneiss came first, the foliation came first, the dike was intruded into the grey gneiss. Now if I take a striking dip along the margins of the dike, I'm getting approximately 120 degrees, which is northwest southeast. That is parallel to the orientation of all of the Scourie dikes in this region here. Now the interesting thing is that this was an intrusive contact, but it has also been affected by later shearing during the Laxfordian deformation, and we can see that in this outcrop just up here. Right, we've just moved a little way along the contact of the Scourie dike here, and in the last outcrop we saw the foliation cut by the intrusive margin of the dike, but here we can see that there's a shearing fabric superimposed on the contact zone. So we have two major shear planes. One is along my hand here, and one is along the margin of the dike here. These are called shear planes or C fabrics. C is the French for cisaillement, which means shear. And this is the schistosity. This is the S plane, which you can see is curving into alignment with the shear. And between these two shear planes, they give us an indication of dextral sense of shear in this direction. So it means that the margin of the dike, after it was in place, was subjected to a small amount of Laxfordian dextral strike slip shear. This is happening deep in the crust in the ductile zone. So now I'm going to take a couple of readings. One is on the schistosity plane, which is here. If I put my compass clino on there and I take a measurement, this is almost exactly east-west, 090 degrees. This is a strike of the schistosity. If I take a strike on the shear plane, which is coincident with the margin of the Scourie dike, it would be approximately 125, which is parallel to all of the orientation of the Scourie dikes in this region here. So we have the sequence of events is the Scourie gneiss with the fabric superimposed by Laxfordian deformation and re-metamorphism, turning granulite facies rocks into amphibolite facies rocks after intrusion of the Scourie dike, and then during late Laxfordian deformation, strike slip shear as we approach the Canis shear zone.
As we move closer towards the Canis shear zone, we see more intense recrystallization, deformation, and later metamorphism of these older Scourian rocks. Now here, the Laxfordian overprint has changed the mineralogy of the original granulite facies assemblages to be amphibolite facies. And in this nice panel, we can see all three of the previous rock types and their amphibolite facies equivalents. Some of these extremely dark regions are more than likely the ultramafic pods that have been spotted before. Instead of having lots of pyroxene and olivine, now we have lower temperature minerals that are more hydrous. Actinolite, talc, chlorite, different forms of amphibole. The mafic rocks that we saw previously, which were dominated by pyroxene and garnet in the exposures at Scourie, now contain none of those minerals. They're amphibolites, sensu stricto, with hornblende, plagioclase, a bit of biotite or epidote perhaps. And the felsic members, which originally contained orthopyroxene in the granulite facies rocks, do not have any pyroxene at all. Those pyroxenes have been transformed to hornblendes and biotites, although they still have the quartz and the feldspar bearing assemblages. The deformation here is quite intense. We can see near isoclinal folding, and this will only get stronger as we move into the shear zone itself.
Okay, we're here just north of Amelvic Bay, and the object of this set of outcrops is to look at deep ductile deformation on a high temperature ductile shear zone. So to explain how this works, I've got here a diagram, very simplified diagram of a continental fault. It could be a thrust fault. In this case, let's say it's a strike slip fault. So at the surface of the earth here, we've got our yaks grazing on the surface of the earth. We have a fault that breaks the surface. So when you have an earthquake, for example, on something like the San Andreas fault, it will start off about here in 10, 20 kilometers depth in the crust, and it will propagate towards the Earth's surface as the rocks are moving along the fault. This is what we call the brittle or seismogenic upper crust. That same deformation is taken up in the lower crust by ductile deformation or aseismic creep. So the rocks deform by ductile flow rather than brittle fracture. Brittle fracture creates earthquakes. Ductile flow is representative of faults deep in the Earth's crust. So each level of this produces different rock types. So along the brittle upper crust, we see rocks like fault gouge, where the rocks are pulped to clay, or breccia, where you have fragments of lithified rock surrounded by clay forming as a result of brittle faulting along that fault. You can get rocks called pseudo-tachelites. Tachylite is the Greek for glass. It looks like obsidian. It's very, very fine-grained, usually black, and it is an indicator of a paleo earthquake. So when you see pseudo-tachelites in the Earth's crust, you know that at some stage that was on a fault, the fault fractured, and during that earthquake it pulverized the rock to form a pseudo-tachelite. At deeper levels, we're looking at cataclastic rocks. These cataclasites include mylonites, which can break up the rock with fragments around it. So you go all the way from proto-mylonites to ultramylonites. Ultramylonites are extremely fine-grained rocks formed as a result of grain size reduction along deep ductile shear zones. Now, a fault at the surface will break very cleanly, which is why you can see them on satellite images of the Earth's crust. But once you go between the brittle upper crust and the ductile lower crust, this fault will end up with a number of ductile shear zones, most of which will anastomose into a zone that could be 5, 10, even 20 kilometres wide. And in between these ductile shear zones will be fragments of rock, of country rock, which are less deformed. So that's exactly what we see in this outcrop here. We're looking at the ductile lower crust of the Canis shear zone. And if I lean over here, we have one of these rocks of the Lewisian gneiss, which is relatively unstrained by the ductile folding. And this is one of these fragments caught between two mobile ductile strands of the fault. If you look at these rocks, these are highly deformed. These are proto-mylonites, and these are approaching this level of the crust, looking at 2 or 3 strands of ductile shear zone encompassing almost xenolithic-like fragments of unmyelonitized rock, country rock. So this diagram shows from the surface of the Earth down to the lower crust. The crust mantle boundary generally is at an average of around 35 kilometres in the continent, at least where there's not mountain building been occurring. And we are looking at the deformation of minerals. So quartz will start to deform plastically at temperatures above 350 degrees centigrade. And this is the beginning of what we call the ductile brittle transition. Feldspars will start to deform plastically at higher temperatures around 450, 500 degrees centigrade. So between these two temperature extremes is where quartz and feldspar go from brittle fracture to ductile shear. And that's what we call the brittle ductile transition. We're now below the brittle ductile transition in this region of the lower crust. So if you take a strike-slip fault like the San Andreas fault, for example, what it will look like in the deep crust is probably something similar to what we see exhumed in the Canis shear zone. Okay, we're standing on a hilltop just north of Amelvic Bay, and I'm looking across the mountains of Sutherland. This is the ascent region of Sutherland, and you can see the big mountains of Sulven, Canisp, Coolmore, Coolbeg, Stack Polly. These are all made of Torridonian sandstones sitting unconformably on top of the Lewisian gneiss. We're actually right on the terrain boundary here between the Scourian granulites to the north and the Laxfordian amphibolites to the south. And we've walked a profile section through the Canis shear zone, which is the bounding shear zone between the two terrains. And I'm standing right along strike. And you can look out to sea, and that far headland, you can see the strike of the banding in the gneisses is very, very steep. I can take a long distance strike by eyeing up my compass clinometer, and it is almost east-west. It's about 108 degrees east-west. And this is the big shear zone. It's maybe 200 or 300 meters wide, separating the hotter, deeper rocks of the granulites to the north from the shallower amphibolites to the south in the Laxfordian. Now, this terrain boundary has had a lot of discussion about its origin and models. One model is that the two terrains were different plates that have been juxtaposed, shunted in along big strike-slip faults like the Canis shear zone. Another model is that they're actually just metamorphic boundaries between deep, hot granulite facies lower crust and middle crust amphibolite facies rocks. This is exactly what we see in big mountain belts like the Himalayas, for example, where today the Archean Indian Shield granulites form the deep crust, and the Himalayan Barrovian facies metamorphic rocks, which would be equivalent to the Laxfordian, form the middle crust. So the debate is ongoing, and it's really dependent on doing detailed structural work combined, of course, with field mapping, combined with metamorphic petrology, thermobarometry, and of course uranium-layered geochronology.